The title of this presentation is Nonlinear Stability and Convergence of a Hyperbolic Scheme for Heat Transfer. The authors are Luis Romeo Martínez Jiménez, José Eduardo Macías Díaz, and Hector Vargas Rodríguez. So this is the schedule of the presentation. I'm going to introduce some preliminaries firstly. Next, I'm going to introduce a numerical model. I'm going to analyze it. And finally, I'm going to provide some conclusions. Let's start with the preliminaries first. I'm going to start with this definition that is nowadays the standard definition of the fractional derivative. Suppose that f is a real function, n is a non-negative integer, and alpha is a real number with the property that alpha is between n minus 1 and n. Then the Riesz fractional derivative of the function f of order alpha is given by this formula, where this is the n derivative and here gamma is the standard gamma function. We are going to extend this definition for functions from R cross this interval to the reals. Then the Riesz fractional derivative of these functions of order alpha is given by this expression. In what follows, I'm going to consider alpha and beta numbers between 1 and 2. I'm going to assume that u is a complex function and m a real function. Moreover, I'm going also to consider u0, m0, and m1 sufficiently smooth functions. Under these circumstances, the fractional extension of the Sakharov system is given by this system of partial differential equations. This equation is a parabolic differential equation, and this is a hyperbolic differential equation. Notice the fractional derivatives here with respect to alpha and here with respect to beta. Alpha and beta are not necessarily equal. This system is going to be subject to initial conditions and boundary conditions of the Neumann type. Notice that in the case when alpha is equal to beta and equal to 2, this is the well-known Sakharov system. In the following analysis, I'm going to consider this auxiliary function b, which satisfies this partial differential equation. Remember, this is only an auxiliary function, and u and m are the solutions of our system. Associated with this system, there is a mass density at the point xt, which is given by u, the absolute value of u squared. There is also a total mass at time t, which is given by the 2 norm of u squared. We also introduce the Hamiltonian. Here this term is the kinetic energy, and here is the potential energy. The potential energy is given by this expression, and this is what we call free energy. The total energy at time t is given by the integral from minus infinity to infinity of the Hamiltonian, and here we have the kinetic energy and the total potential energy. Total potential energy is given by this expression. This system is such that the total mass is preserved and the free energy is non-negative and also conserved. The proof goes as follows. We take the inner product of the first equation with u. Then we take the imaginary part and we get this expression, which is the derivative of the total mass. Then the mass is conserved. For the second part, we take the real part of this inner product. Notice that this is the second equation, which is also equal to 0. Then all this expression is equal to 0. But this expression can be written in the following way, as the temporal derivative of this expression, which is the free energy. It is also the derivative of the free energy, thus free energy is also conserved. We are going to establish the boundedness. It follows from the fact that the free energy is conserved. Then it follows that there exists a constancy which depends only on the initial conditions. Hence, the free energy is bounded by this constant. In fact, these several terms are bounded by a common constant when the boundedness of the system follows. We are going to skip the proof since it's rather straightforward. The total energy of the system is dissipated. We compute firstly the derivative of the equation 3. Next, we take the imaginary part of the inner product between that derivative and this partial derivative, and we get this expression. Then, using the property of the conservation of free energy and the last identity, we notice that this derivative is equal to this expression, which is not necessarily conserved. Then we conclude that total energy is dissipated. About the numerical model, in order to approximate the fractional derivative, we are going to use fractional center difference. If f is a function and g are a sequence of coefficients given by this expression, then the fractional centered difference of the function f of order alpha in space is defined by this sum and the coefficients when alpha is between 1 and 2 satisfy these properties. Moreover, fractional center difference provide consistent approximation of the fractional derivative of f of order alpha with consistency order equal to 2. In the following, we are going to discretize the continuous problem. So we are going to consider a spatial step size h and a temporal step size t. We are going to consider also uniform partitions of the spatial interval and the temporal interval. We also are going to use capital letters to denote the numerical approximation of their respective functions in the continuum problem. We introduce the classical inner product, the classical p-norm, the classical infinite norm. We introduce discrete operators, so most of them are actually standard operators. So these are difference operators in space and time, average operators, and this is the way we are going to approximate the fractional derivative of order alpha. As you can see, we are using fractional order center difference. And we recall this lemma from the literature, so this lemma is basically integration by part. It tells us that the inner product of this operator applied to U with P is equal to this other inner product. The proof of this result is established using the fact that this operator is self-adjoint and non-negative, thus it has a square root operator. These are other results which are available in the literature and which are going to be useful in the following. The numerical model to approximate the continuous system is provided by these expressions. This is the approximation for the first equation, this for the second equation, and these are the initially boundary conditions. Okay. And the first result is the solubility of the system. It turns out that the discrete model is solvable for any set of initial conditions. To do that, to establish the solution for capital U, we need to use Browder's fixed point theorem. And so motivated by Browder's fixed point theorem, we define this function, which is essentially the finite difference scheme, where we are given the unknown eta for the new time, and we take the real part of this inner product and notice that these inequalities are satisfied. So far, for suitable lambda in Browder's fixed point theorem, so these hypotheses are satisfied and thus there exists a solution for the system. For the solution of the variable m, it's quite easy because the system is linear. Actually, it can be represented in this form by this matrix A, which is a diagonal matrix, and this vector B. And this system is obviously going to have a solution. So the solution of the finite difference scheme exists as and is unique. Okay. We introduce a discrete form of the Hamiltonian and the total energy. And this is one of the main results. The discrete mass of the system is actually conserved. Okay. The proof of that is very similar to the continuous case. So we take some inner product which are equal to 0. And we take the imaginary parts, and using some algebra we obtain this result. So the right hand side is 1/2 of the discrete derivative of the mass with respect to the time, thus the mass is conserved. Also, the discrete free energy is conserved when tau and h satisfy this property. And the proof is a little bit longer, but the idea is the same as in the continuous case. We take some suitable inner products. We take real part that's going to be equal to 0. We calculate from the inner product of each of the term, and we use the fact that h and tau satisfy the condition mentioned in the hypothesis, and then the energy is conserved. Moreover, the total free energy is also greater or equal to 0, which is in agreement with the continuous case scenario. Okay. The boundedness follows readily from this fact. More precisely, it follows that these quantities are bounded by this term on the right-hand side, and you can bound this using the previous theorem by a constant C0, which only depends on the initial condition, and thus various terms are bounded. We are going to skip the proof since it is from mathematical induction. As one of the main results, we compare this continuous operator with these discrete operators in order to establish consistency under suitable regularity conditions on the solution. So it is possible to see that these discrete operators approximate the continuous operator with consistency order equal to 2, and that also happens for the discrete energy density. To establish stability, we need a discrete form of Grant-Wells inequality, and this is stability. So you consider two sets of initial conditions with corresponding solutions U and M and U tilde M tilde. You define these differences, epsilon and zeta. You define omega in this form, and you can check that omega is bounded by this term. I'm going to skip this proof. Uniqueness is a particle consequence of stability, and in similar fashion, we can establish converge if U and M are sufficiently smooth. Then the solution of the numerical model converges to that of the continuous model with convergence order equal to 2. To produce our simulation, we will impose homogeneous Neumann conditions on the boundary P, along with the following set of initial conditions. As a matter of fact, it's worth pointing that these functions are the initial condition for an exact solution of the well-known Klein-Gordon-Sakharov equation. This solution that has been previously derived by other authors. It can be found in the literature. The only simulations we are going to provide in this case are with respect to the mass and with respect to the free energy. As you can see, as a result of our simulation, the mass is conserved and free energy is also conserved in agreement with the results that we derived in this study. And now, other simulations have been produced also, but they have not been reported in this presentation due to the limitation of time. But in those studies, we have proved that the finite difference scheme converges to the exact solution with convergence order equal to 2. As conclusions, so here we provide actually one finite scheme to solve the mathematical model. Discrete energy functionals were proposed for the model, which showed that the model is consistent and stable and convergent. And the results show that the method approximately preserves the energy of the system. To guarantee the existence of solution of the implicit method, we have to impose various conditions, but those conditions are satisfied in terms of the computer parameters, and the variation in the total energy associated to the explicit scheme is smaller. Thank you very much.